Good morning, mathematicians. We're facing a very serious issue today. That issue is, of course, that last night when I was at the grocery store, I looked at the section on coffee and I said, no, I have more coffee at home. I'll wait till the next time I'm near the other grocery store that has the better coffee. I'll be fine. I've got a whole other bag. Well, that turned out to not be the case. Evidently, I only had. Really, I probably shouldn't have filled the liquid up this much. That's not enough bean for even that much liquid, but I'm trying to draw it out. That turned out to not be the case. So that's what we're dealing with. Hello, Onage Effects. So originally, I had wanted. I was like, oh, it's Saturday. I'm gonna start late. I'm gonna. Hello, Jonathan Groob. Welcome back. I was like, it's Saturday. I'm gonna start late. I'll do a long stream. But with this coffee situation here, does coffee help with a 4-hour sleep? What does it like? Does it help you get to sleep and experience a 4-hour sleep? Maybe if you have ADD. But otherwise, probably not. So, anywho, that's the deal, and we may not go on that long today because of my coffee. The bright side is it's a chance for me to go experience the coffee shop down the street that I haven't been to since I moved to this area. So, there you go. You slept 4 hours yesterday, couldn't study. Brutal. My sleeps have been bad lately, and I'm not sure why. I think I might cut out dairy again and see what happens. The homework that I gave you, you couldn't do it. What was the homework that I gave you? Can you remind me? Hello, Rod. Dodgers lost game 1. What has this world come to? A correct and just place. Leo lectures, a correct and just place. Hello, Bueller. Is it just you or those tensors italicized? The tensors? Oh, God. Oh, yeah. What the hell? How do you even do that? Wild. Also, what's going on with the tip of the arrow here? It's got like a little detail in it? What the hell? Who the hell typeset this? Prove that was a functor? Oh, right. Okay, so what part are you struggling on? You need to prove it's a functor. I mean, I told you what it does on objects and maps. So which part? I mean, there's what? To show it's a functor, you need to show two things. Can you tell me what those two things are, and can you tell me which one you're struggling with? As a Langlands program enjoyer, do I have any experience with Dr. Wushi Goldring? No, never heard of him. You're asking because you're applying to a PhD position of his. Yeah, sorry, I'm not familiar with the name. There's a lot of people that fall under the umbrella of Langlands, so yeah, very weird. Like, maybe they were put here in typesetting using the alt code instead of a slash O times. You know what I mean? Or Unicode. It maybe was put in as a Unicode character and then got italicized in there. I have no idea. That's the only thing I can imagine. Thing 1, it's like super cool and chill. Thing 2, I don't know. Okay. No, the Schulze style Langlands is kind of different. It's very much more like stacks and infinity categories and stuff. Although I would be interested in finding the connection between my group's version of local Langlands and their version, because there is a connection. Like our version should just be some localization of their version. Right, preservation of composition and identities. So which one of those did you manage to do? One of them, ownage effects. Also, I should go into my YouTube live settings and change latency to ultra low. Okay, I don't know where those settings are. I'm not going to do that now. Can you just change latency as a setting? I thought it was just a feature of like it takes processing power to do, so I'm naturally going to be a couple seconds behind. Have you ever done some quantum problems? I did take a particle physics course in my undergrad. Not a single one. Okay, well, let me ask you this. So, the default is like 10 to 15 seconds behind. I see. Well, maybe I'll make you pay premium to talk with me in real time. I'm kidding. Okay, well, I told you where this map goes, right? So, I mean, take the identity function from G to G. And what do we need to do? We need to check that it's the identity on this ring. So you need to check that it's the identity on the basis of indicator functions. So id tilde, according to this formula that I gave you, applied to 1G is what? Okay, so we've got a graded algebra. Concentrated, it's just the rational numbers concentrated in degree 0. If V star is x2n, is the span, is the polynomial ring in here with, I'm assuming, the natural grading, the grading of powers of x. W star is the exterior algebra generated on y with odd coefficients, odd numbers. So maybe it's not the usual grading. Powers of x is considered some even number, and y is considered some odd number. Hello, Kastakakori. Id G? What does this formula say? So remember, it's a functor. It's a functor from the category of groups to the category of rings. Right? So if I start with some map phi between two groups and I apply my functor, I should get a map between two rings. Right? So here I'm starting with two groups, the identity homomorphism between two groups. And this function that I get out should be a map between that functor applied to G and that functor applied to G. In other words, I should be getting a map between the rings KG and KG. So id tilde should go between these rings, right? And here, right here, is the definition for phi tilde, right? So I'm applying phi tilde to a function, and I should be getting out another function here. And this white box tells you exactly how to compute that function. So I'll let you think about that for a minute. If V star, wait, what? What? If V star is isomorphic to this and to this? Okay. Then W is also isomorphic to this. To Y2N. Oh, to X. If it's isomorphic to this exterior algebra with this kind of grading, this is such a confusing setup. Remember, you have to do italics tensors to preserve grading. Otherwise, it is forgotten. Huh? What? Oh. Sorry, thanks for letting me know. You guys can't see the whole statement. Oh yeah, maybe that's what he means. Maybe is it skew tensors for, or italicized tensors for skew algebras? Maybe that's his hidden convention here. Right, exactly, Onage. So, so now this is just the indicator function of the identity applied to G, but the identity applied to G is just G. So in other words, n tilde maps each of our basis functions back to themselves, and so it is the identity function on the entire ring. So we've confirmed that, in fact, this functor I described last time sends the identity map from a group to itself to the identity map on the ring of functions. Now, the other thing you need to check is that it respects composition, right? So now you suppose that you have phi and psi, and you want to check that phi psi tilde is equal to phi composed with psi. Oh, I put things backwards. I always do that. Psi phi, I love saying that, is psi tilde composed with phi tilde. Well, how can you check that? Well, again, instead of checking on arbitrary elements, it'll suffice to check it on the basis, because this ring is in algebra. And so you can plug in this to both sides, and I'll leave it to you to do the computation and verify that these things are equal. I mean, I shouldn't write this equal sign yet because we're trying to figure out if they're equal, right? So let me put this here, and then I'll leave it to you to put equal signs down here until you get two things that are equal. To be honest, is our notation backwards? I don't know. Speaking of Professor Cockett, who came up yesterday in stream, he has very strong opinions about doing it the less conventional way, and is sure to say as much. Yeah. Okay, so this is a simple case of Borel. Oh, okay. Yeah, no problem, Onish. Give it a good solid try, and let me know if you're absolutely stuck again. So in particular, the reader can compare this example with these two theorems. Okay, sure. Okay, let's see if my understanding is correct. No, there's no way in hell that it is, because why is n on the 0 axis? Okay, maybe this doesn't have to be 0, but it's just, I don't know, I'm confused. And why does y go to x? Is this on the E2 page? It must be, because we always start there. Wait, this is 1 here? 1, 2, 3, 4? No, that can't be right. Y is supposed to be... Y is supposed to be an odd degree. Oh, but W is the exterior algebra. Wait, let's go back up. How are we setting up right. X has to go to Y, otherwise they would both survive to infinity. Yeah, but your logic, I don't understand your logic, because we didn't suppose whether or not they both survive to infinity. Like, isn't that something we have to prove? Like, given our assumptions on this thing, shouldn't we have to prove that they go to infinity, survive to infinity or not? Like E2 PQ should be WP tensor WQ, right? H star is Q. Yes, H star is Q. In this working backwards example, they tell you what the E infinity page is supposed to be. Oh. They do? Oh, suppose theorem 4 holds. Okay. I see. It's supposed to be Q in total degree. It's Q in total degree 0 and 0 everywhere else. Right. And I mean, H... Okay, why though? What's a bi-graded algebra? It's well, this is an algebra. This is an algebra. I mean, you should go back. I think we covered it yesterday or the day before. But basically, it's just you've got two pieces affecting the grading, and then the total grading is the sum of those two things. So that's just like That's just like a bigraded vector space or something, but then you also suppose that there's some compatible um, algebra action. So generally that you have some graded algebra acting on it in a compatible way. Okay, if it converges, then yeah, what does that mean again in terms of H? If it converges to H, I'm forgetting these like basic definitions now. Converging to H means that if E infinity is isomorphic to, yeah, hang on. What was the original definition? It's said to converge to H if this is true. Right. So what was our formula? E infinity PQ is FP HP plus Q over FP H1 P plus Q, which is H E0 PQ H star. Right. Since you're working over field, you can really just identify H star with its associated graded, which is E infinity. Huh? I can identify H star with its associated graded, which is E infinity. Yeah, what is, let me recall, the associated graded is just, what was our definition here? E0, well, it's supposed to be, we're supposed to have H P0 infinity E0 P H star. Right, where EP0. Right, that's just this. That's just, yeah. Okay. This is more or less vector spaces have basis. Sure. I need to do the explicit computation to understand it. Okay, where were we here? Past this. I should remember the page number. That would have made life easier. Okay, we're back, finally. We are so back. Okay, so we're saying that this converges And so we know, for example, so in degree 0 we have Q. In degree non-zero, if n is not equal to 0, then 0 is Hn, which is the sum over all Fp Hn mod Fp plus 1 Hn. And so it had better be that every P Fp Hn is Fp plus 1 Hn. Oh, but of course, because we defined it to be trivial. Okay, so that, I don't understand how this gives us any information. But then we know that Q should be the sum over Fp Q Fp plus 1 Q, and then Fp is right, it's just that. So what does that mean? It means only one of these can be non-zero. And FPQ, but we define this a different way, right? It was like, this is supposed to be like FPH star intersect H0, something like this, which is just Q. So, I mean, doesn't this just tell us that there's like one P somewhere where the gratings, where the filtrations aren't equal, and then, yeah, I don't get how I still don't get how we get from there to Y being mapped to X. Well, let me keep reading, and maybe... if I have I missed something here. If I have a filtered vector space and I pass through its graded space, you can give an isomorphism back to the originally chosen basis that respected the filtration. Okay. Recall the differential applied to an element written as W tensor Z satisfies the Leibniz rule. Okay, so at least maybe we'll understand the tensor of two elements here. Oh, right. I see. Hang on. This should be on the line. This should be on the line tensor 1. No, I don't get it. If it never maps to X, it never dies on any page. And then you have a non-zero thing in higher degree. But why would it have to map to X? Like, why can't it map to X squared or something? Like, yeah, this is what I don't get. So Y2N, I mean Y2N plus 1 should live in degree, well, I guess it lives in E2. I mean, he's not writing a tensor there, so I don't really... E2, but it has to be one copy of V, because unless, are we saying that if you tensor something with itself 0 times, then you get the one-dimensional vector space? E2 something 1, right? Because the first exterior power. The differentials going out of Y can only land in those. But why? But why? I mean, where does Y? So first off, where does Y even live? Y, and I'm confused about the subscript notation here. So we're tensoring over. This is W1, right? So this should be E2, comma 1, because this just lives in the first symmetric power, right? You mean the indexing of the picture. But why is Y in 0, 3? But why is Y in 0, 3? That does not make any sense to me. That does not make any sense to me at all. Like, based off of everything else we've said here, how can that even be true? Like, actually, so what does sim of Y even mean? Because we just have one Y spanning it, so shouldn't sim of Y be 0? Like, sim 3Y should just be the span of Y, wedge, Y, wedge, Y, which should be 0. What am I missing here? Well, one has the second page is. Yes, I agree with you there, right? I agree with you there. The second page is V tensor W. Okay, let's see. I guess I'm confused about what degree things are supposed to. I guess I'm getting confused with the degree and the indexing here. Y has degree 3. Wait, why is it degree 3? So we've suddenly chosen n to be equal to 1? Like, I don't understand. I don't understand. Y wedge Y would be degree 6, but Y wedge Y is 0. But Y wedge Y is 0. How can... Okay. So for some reason, we've just decided to mysteriously set n equal to be n to be 1 in the picture. Okay. I see. Okay, so n is equal to 1 in the picture. Okay. Fine. So n is equal to 1 in the picture. Okay. But in which E does Y live? Because if I'm thinking about it this way, right? Y is going to live in some grading, right? Some VP tensor WQ. And let's figure out where that is. So this is going to live in the X2N graded piece of this. And it will be somewhere in... Actually, I'm even confused about what the wedge is supposed to mean here. And it's going to live somewhere in Y... I don't know, I'll call it Y3, I guess, and X2. Right, but where does it live? It lives in E2, and I'm trying to find the indices of E2 that it lives in, right? It lives in E2 PQ for some PQ. We need to figure out what P and Q that is. So to figure that out, I'm unpacking the definition. So I'm here. And okay. Y lives in degree 3. Okay, right. So the zero part of this is just Q. This is P equals 0 is just the Q. And if I take the 1 part of this, it's just wedge Y3. So Y3 should be in there, I guess. Right. I guess I'm still confused though. Right. Okay. So I'm happy with the fact that Y lives in 0. Wait, but this it's 0, 1, right? Q should be 1. Q should be 1. Why is this I'm No, but it's the third degree part. Okay, sorry. Q should be 3. I'm very confused by this. The degree 1 part, right. The degree 1 part is 0, right. Y lives in the degree 3 part. Okay. Sorry. Right. Okay, so we apply the differential to Y. This has to live in E2, 2, 3 minus 2 plus 1. Right? It must. Nope, that's not what we see. D2. This is not a picture of the 2 page. I see. But that group is 0. This means Y survives into the next page. Then the same for D3. Okay. So why does Y go to X? Only in D4 it hits X. I see. Only in D4. I see. So, right. So D, okay. Well, let's also think, though, it survives, right, everything's 0, so Y survives, unless, I mean, the image of the map going into 0, 3 could be everything, but no, that thing is 0. So, right, y definitely survives to the next page. So we can think about y as now being in E3, 0, 3, right? And again, we could compute d2y. Wait, how did we know that E222 is 0? I guess just by, right, I guess just by account of the grading. Okay, and then D3 of y is going to wind up in E3, 3, 1. And so let's figure out why this is 0. Because we're taking an odd graded part of like an even thing. Okay, so for similar reasons, it will survive. Y then survives onto E4, 0, 3, where now this differential will be in E4, 4. 3 minus 4 is minus 1, 0. Will this not be 0 as well? Because that's what? V is... this is x2 tensor wedge y 3. This is the 4 part of this, and this is the 0 part of this. Now I'm confused again. Right as Arad said, I think you got it. Yeah, now I'm confused because shouldn't this be 0? And certainly, how could it possibly contain x? Shouldn't it be x squared? Shouldn't it be x squared? Did I compute the differential wrong? 0 plus 4 is 4. 3 minus 4 is minus 1, plus 1 is 0. Yeah. Now I'm lost again. Okay, let me read ahead a bit. I'm out of coffee, so... Oh, no, there's still a little bit left. Okay. Recall the differential applied to an element, written as Leibniz rule. Further, the differential restricted to this is null. And restricted to this, its image must be... The differential restricted to V star is null. Why is that? Oh, because we're taking an even part of an odd thing. So fine. Is null and restricted to this. Its image, it must have image in here. Yeah, everything has image in there. What? I don't know what you mean. You think McCleary made an oopsie? X should have degree 2n plus 2, surely? Maybe. then I mean that would fix that would fix where I was being confused. Yeah, that would fix where I was being confused. Then if we take the differential of this thing, or we're saying, okay, we're taking one tensor u, we're writing its differential as this, and then we're saying, well, from there, the differential of uk is, why does this follow? Why does this follow? Why does k come out in front here? What are we? Oh, okay, because I guess maybe just general Leibniz rule nonsense? But UK, but that's different. No, now I'm confused. Like, if this meant u tensored with itself k times, I would be happy that this comes out. But the Leibniz rule is on tensor products. Oh, sorry. Yes, but okay, but we're right. So right, because this is one tensor u multiplied by itself k times. Okay, great. It looks like it's off by 1, but you wouldn't be confident because you're not paying close attention. Okay. Good. I just need to keep in mind that sometimes McCleary makes mistakes, and that's why I'm losing my mind. Okay. Oh. Okay, we've gotten through a bunch of this. In the first case, V star is this, and we can display the E2 term in the spectral sequence converging to this. Side note, I wonder what you guys think. I'm applying for postdocs, and the teaching aspect is important, more so to some places than others. But I was thinking that my video where I say I'm making fun of crackpots, that could kind of be a bad look as a teacher, right? And that's now become one of my more popular videos. So I wonder if I should take that down. I wonder if I should remove that video. I don't know. It already had its run. I don't know. Maybe if I just change the thumbnail or something. I don't know. Yeah. Well, maybe I've talked about my YouTube channel in my application. In my applications. So it's possible. It's possible. They could go there and they could see it. Like, if you go to my channel, it's not always the first thing that pops up, though, right? Like, well, let me see. Let me start a incognito tab here. Go to YouTube. I mean, if you go to the channel, I mean, I guess it's not the first thing that pops up anymore. Like, it's not necessarily the first thing that pops up, so maybe it's not. Maybe it doesn't matter, right? I mean, they'll see these things and maybe they'll be like, what the hell? But, you know, they'll also see this and this. I don't know. They got to read 100 plus postdoc apps. But yeah, it is possible. Yeah, I don't know. I gotta think about it. Oh my god, I'm live right now. Oh crap. Okay. Let's try and get to a natural stopping point here. Oh, we got a lot more to do. okay, we've already learned a lot today. I feel like learning equals just sitting and being frustrated. You got to admit you haven't watched those crackpot Vixor videos, so I did a bad job anyways. Maybe it's just you, though. There are other people who seem to like it, yeah. Yeah, I was thinking about making another one where actually I found some papers that, because some of them are just like obvious total nonsense, and probably these are written by people who are mentally unwell. But I did find some papers that are like, I'm not sure if they're totally correct, but they're maybe not totally crackpot because it's just people like proving random weird little theorems that, aren't anything that anyone would put in a paper. But it's still like, they're not claiming to have proved to the Collatz conjecture or something, You also haven't seen those videos, but they are. How can they be your favorite work of mine then? Just by assumption. Interesting. Well, you know what they say about assuming. Okay, in the first case, V is this, and we can display the E2 term in the spectral sequence converging to this. As on the opposite page. What? The opposite page? As on the opposite page? What is the opposite page? Did you mean the previous page? What the hell are you talking about? And why are you saying K? Don't you mean Q? Oh my god. I'm gonna lose my damn mind. Since x2n does not survive to E infinity, right. Right, because it gets hit by Y. So it's in the image eventually. There must be a y2n minus 1 in W. Ooh. Huh? Oh, there must be a y2n. Why? How? How can there be a y1? Time to print the paper double-sided. Oh yeah, that must mean opposite page of the book. What does that mean? Now he's saying y is 2n minus 1 instead of 2n plus 1. Yeah, okay, good. That's just another typo. Oh, good lord. Yeah, is this a sign that we need to change books soon? I don't know. I feel I kind of want to keep going with this book, but Hill said this, McCleary should really have gotten the indexing right on this, especially for like first simple example spectral sequences. Yeah. You would think that section 1 would be the most important, like later chapters, whatever. You're tired, you're taxed from writing a whole textbook, but McCleary wrote a book titled User's Guide to Spectral Sequences. Books traditionally consist of pages. Yeah. I mean, yeah. That's true. Agreed. Okay. Well, I don't know. With all the confusing indexing, is it even worth going through this now, what he's saying? Let's okay. If he's ignoring the indices, let's go ahead ignoring the indices and just get the idea of this proof. Thus, we get the pattern of differentials in the picture. If W star contains any other elements, it would give rise to classes that would persist to E infinity and contribute to A star. Thus, this has to be true. Okay. To treat the other case, we consider some other diagram. Okay, maybe we should work this out for ourselves or something. When someone gets what is going on with spectral sequence calculations, it's not the biggest deal to get minor indexing things wrong here. Sure, when someone gets what's going on with spectral sequences. I'm not that someone, and I'm reading this book, and I'm only on page 35 of this book precisely because I'm someone who doesn't get what's going on with spectral sequences. That's kind of the whole problem here. But in the beginning, yes, exactly. It does matter. Yes, exactly. Frankly, you don't think McCleary's book is worth it, even disregarding the typos? It's a great reference. Actually mentioned some really obscure stuff, but terrible intro. Yeah. Sorry, I saw your comment, Leo. Yeah. I don't know. Should we be changing books then? What's the community consensus here? What do you guys think I should be looking at instead? Okay. Notice that the characteristic of the field plays a role here. Yeah, so we had those denominators. For fields of non-zero characteristic or for an arbitrary ring, the simple procedure can lead to elements that persist to E infinity unless W star is different. For such cases, W star would have the structure of a divided power algebra. Yeah. You don't have a reference you would point to for spectral sequences. Yeah. Okay. Gosh. Here's some other example, which the indexing's probably wrong on again. Yeah. Okay. Well, maybe that's just a place for us to leave it for now. I think I do have some other sources on spectral sequences downloaded that we could consider. Oh, this is a good exercise. I do want to do this exercise. Prove the 5 lemma. Well, it's interesting. I mean, you can just prove the 5 lemma normally, but there should be some way to do this. There should be some way to do this with spectral sequences. I've been told. So, I mean, that's a fun exercise. But the 5 lemma, one of the 3 things from homological algebra. Yeah. Oh, you downloaded the book and it skimmed the intro and said you corrected many errors from the previous edition. Yeah. Viable if you care about algebra. If you care about topology, pretty much any algebraic topology book. I think I do want to focus more on the algebra. So, maybe we will switch over to Viable. But I thought Viable had a good chunk of algebraic topology too. No. And let's look at I mean, maybe now that we've gotten our hands dirty, we could go back and look at this article and then maybe try to like, I've got a book somewhere here. I've got this book, Topological Methods in Galois Representation Theory. And Let's see. There's. I mean, I don't know. Might be harder. It seems like a bit of a rare book. Might be harder to dig up a PDF copy, but um, I think it mostly deals with like non-abelian cohomology. But definitely, I remember seeing some spectral sequence arguments in here. I remember seeing some spectral sequence arguments in here, and I do wonder, like, maybe if we go through this review document, we might be in good shape to then track through an example. Like, that might help me anyways. Oh, spectral sequence calculations of some cohomology rings. So I'm just going to pull it up. Yeah. So maybe if we go through this and I mean, I can just try and repeat. I mean, it's not as it's nice if I can put the textbook on screen, and then maybe. But I could always just have it open and then reproduce the details here for you guys. I don't know, but there's a lot of nice spectral sequence calculations in there, so. Everything is the snake lemma, yeah. Found a PDF for it? Oh, nice. Okay. Yeah. So maybe that's the best way forward. I kind of want to review this. Oh, you know what I might do? Actually, we could review this, but I wonder, does this document, where does Weibel talk about, because one thing actually because just looking through that, I want to, it seems like there's employed the use of triples, of exact triples or whatever, and there's some way to get a spectral sequence out of those. So maybe it would be good to just review those first, because that gets used. So is that in here? Does Weibel cover that somewhere in chapter 5? Or exact triangle, exact couples? What's the? Like it's in Aloofy here. Definitely don't start with those. Well, but I mean, when I opened the book, they were using it. So, yeah, maybe I shouldn't start with those, but definitely I'm forced into those either way. Where are we here? Double complexes. No, it's in the last chapter. Maybe we should have gone to Aloofy. Aloofy's nice and clear. Maybe we should have gone to Aloofy. Maybe we should still go to Aloofy. Yeah, triangles. Yeah, exact triangles. And from exact triangles, you can get spectral sequences. Maybe we should look at Aloofy. What do you guys think? Aloofy next? Maybe. I kind of want to. But I don't know. You're just saying the construction would look really unintuitive before seeing how the spectral sequence itself runs in examples? Okay. So maybe are there examples here in Weibel that we could start with? I guess Leray Serre. Let's just start perusing this. and see where we're going. Maybe there's some, yeah, Leray-Serre. See, look, there's algebraic topology here. We've got a Serre fibration. We've got something here. And we're talking about the Leray sequence. I mean, I'd be willing to just accept this, but I've never seen the, I've actually never gone through the proof of this statement, but, I hate it when I do that. Exact sequence, Yeah, I mean, maybe we start here, I don't know. Could even compute cohomology of something you know otherwise. Actually, someone, a viewer sent me their thesis. I think, did they say it was an undergrad thesis or master's thesis? I don't remember. Maybe it was even a PhD. I don't remember. But they computed some like cohomology of SUN or something. Using spectral sequences. And maybe that would be a good thing to look at because, you know, especially if it is an undergrad or master's thesis, generally those are required to be quite detailed. So that could actually be a good thing to go take a look at. You can also prove Knuth formula stuff with spectral sequence of a double complex. Feibel gives this as an example somewhere. Okay. Well, we'll see. We've just been yapping for a while now. But we'll see what I land on tomorrow. We might crack open that thesis and take a look. That might actually be where we go. So, until then, go get yourself some coffee. That's what I'm about to do. And thanks for bearing with me through my confusion.